Now, did you know that there's an astronomical object in which space and time actually swap places? How does that work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs? The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you would see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet, the circle of light is growing. It gets bigger and bigger in size until finally it turns into a giant circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we captured the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone, and time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back in time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead, and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Well, take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She can literally influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing, travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends and the slower time goes. What does it mean? Well, for example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity. Right. But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now, imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole. A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend toward the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more, and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it gets so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards. What kind of nonsense is that, you may ask? It'll be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in the spaceship who watches you doing this for some reason. At first, for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything's okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling, all because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place, it's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now, it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did. Because in space, you can now only move forward, as if along a straight line. And time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. Why don't you go first?
Black holes pull everything inside they see. You'd better not approach the asteroid belt between Mars and Jupiter. It's extremely hazardous. The sun is yellow. All these statements seem to be universally believed, but are they true? No. Let me tell you the real truth. When you look at the images of the sun, it may seem that our star is on fire. But in reality, the process of burning needs 3 components: heat, fuel, and oxygen. The sun does have some fuel since it's mostly made up of hydrogen and helium, and the former is highly flammable. The star also produces enormous amounts of heat energy, but there's no oxygen in space. So, as you see, the fire triangle remains incomplete. So, instead, the heat and light the sun generates are the result of thermonuclear fusion. Now, about those black holes. You probably know that their gravitational pull is so powerful that not even light can escape their clutches. In other words, you might be imagining a black hole as a giant cosmic vacuum cleaner clearing vast areas of space. But in reality, black holes behave just like any other supermassive object in the universe. The speed you need to escape from the gravitational pull of an object, be it a black hole or a planet, is known as the escape velocity. If we take our sun, which has a relatively modest gravitational pull, you'd need to travel at a speed of 384 miles per second to get away from it. If your spaceship couldn't achieve this speed, you'd fall back down to the surface of the sun. But at the event horizon, aka the point of no return of a black hole, even something traveling at the speed of light wouldn't be fast enough to get away. And still, if there was an object that could move more quickly than the speed of light, it would most likely manage to escape, even if it had already crossed the event horizon. The asteroid belt between Mars and Jupiter isn't a region of hectically moving and constantly colliding large rocks. If you ever found yourself there, you would see how empty and calm it is. The asteroids are so far apart from each other that the chances of collision are laughably small. If you were traveling by spaceship, its radar would easily detect asteroids and would help you avoid them. The vacuum of space is not always cold. It depends on where you measure its temperature. If it's a totally dark, freezing cold part of our universe, the vacuum of space can get as cold as minus 454 degrees Fahrenheit. But if you travel closer to the sun, your thermometer will show a boiling 250 degrees Fahrenheit. The sun seems to be yellow, which is confirmed by the photos of our star. But it's just an illusion. The sun produces all wavelengths of visible light. That's why its true color is white. But when sunlight travels through Earth's atmosphere, it changes. The wavelengths of light at the blue end of the spectrum are way shorter than those at the red. That's why collisions with particles in the air are more likely. That's why during the day, blue light scatters pretty high in the atmosphere, hence the trademark blue color of the sky. That's also the reason why the sun looks yellow. Comets' tails always show which way they're heading, right? Well, it's not that easy. These space travelers are essentially lumps of dirty ice. While approaching the sun, they heat up, releasing dust and gas. If it was happening on Earth, we could expect the resulting tail to point backwards. But in space, there's no air. And since comets are shaped and blown by solar winds and radiation pressure, their tails always point away from the sun. It happens like this. High-energy ultraviolet light collides with the evaporating gas of the comet, taking away electrons and producing charged ions. They get caught up in magnetic field lines and dash away from the sun in a beautiful blue ion tail. Mount Everest is considered to be the tallest mountain on Earth, but it's only true if we speak about its height above sea level. If we take base to summit height, the tallest peak on the planet is Mauna Kea on the Hawaiian Islands. Everest rises 29,035 feet above sea level. For Mauna Kea, this number is a mere 13,800 feet, but a large part of it is submerged, and the mountain's total height is 33,500 feet. That's almost taller than Everest. Our planet does not orbit around the sun. What's going on is the sun, Earth, and all other planets moving around the common center of mass of the solar system. It's indeed very close to the sun, but not exactly at the center of the star. When people think of ringed planets, the first thing that comes to their mind is Saturn. But this gas giant isn't the only planet with rings in the solar system. Jupiter, Uranus, and Neptune all have their own sets of rings, but they're much thinner and not so visible from Earth. But even though Saturn can boast the most impressive rings out there, Neptune's moon Triton may be torn apart by tidal forces in the next 100 million years. If it happens, Neptune will have a dramatic new ring system of its own. Despite a common misconception, Earth is not quite round. Isaac Newton first suggested that Earth was not a perfect sphere in 1687. And like many of his other ideas, it turned out to be true. Basically, we live on a squashed soccer ball. The world is flatter at the top and bottom and bulges out a bit in the middle. But the difference isn't all that great, so this belly is really tiny considering Earth's size. This unusual shape is caused by the way Earth spins. The Moon doesn't really have a dark side. This natural satellite is tidally locked with Earth. That's why we always just see one side of it. There's a misconception that volcanism makes tectonic plates move by pushing them apart. In fact, it's quite the opposite. Tectonic plates' older edges are denser and cooler. This eventually causes them to sink deeper into the mantle of our planet. When two tectonic plates get pulled apart during this process, ocean ridges appear. It also results in volcanism. It's not the Moon's gravity that causes the tides. Earth's natural satellite does pull on the water in the oceans, but this tug is more than 10 million times weaker than the gravitational pull of our planet. What creates the tidal force is the gravity interplay between Earth, the Moon, and the Sun. Plus, it's more of a push than a pull. Is Mercury the hottest planet in the solar system? It seems logical. Mercury is the closest to the Sun. Therefore, its surface temperature must be higher than that of all of the other planets. But in reality, the hottest planet in the solar system is Venus, despite the fact that it's more than 30 million miles further away from the Sun than its neighbor. The average temperature on Mercury is around 333 degrees Fahrenheit, whereas it can reach 867 degrees Fahrenheit on Venus. The reason for this is Venus's atmosphere. Mercury has practically no atmosphere, whereas Venus has a very thick one made up almost entirely of carbon dioxide. This creates a strong greenhouse effect, trapping all the sun's heat and making Venus incredibly hot. There's another myth that claims that a human would explode in space without a spacesuit. In reality, our skin is flexible enough to keep all of our internal organs in place. But in the absence of external pressure in space, the blood in the human body would boil. As a result, the body would expand in size, but it definitely wouldn't explode. And the main problem for a person without a spacesuit would be the lack of oxygen. The simplest way I can explain the concept of a wormhole is this. Try to picture a real earthworm eating its way through an apple. At one point, you'll see one part of the wormhole sticking through the top of the fruit, while its rear end is poking through the bottom. In this example, the worm itself acts like a tunnel, which connects two places in space, or two different places in time, or even a combination of both. In theory, a wormhole could help you travel to the same place you're at right now, but years ago, or instantly transport you to another continent. It can also help you travel back to when the ancient pyramids were being constructed. The concept was first theorized in 1916. Though back then, people didn't call them wormholes. It was then studied by Einstein and his fellow scientist Nathan Rosen back in 1935. But it all started with Einstein's theory of general relativity. He had a hunch that Isaac Newton's idea of gravity as a force wasn't completely right. So he began working on many different experiments to prove his theory. In the simplest of terms, Einstein's theory of general relativity says that gravity is a curving or warping of space. The more mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. Because of the ball's mass, the rubber sheet under it is warped under the weight. It's the same with our sun. It's big enough to curb space across our solar system. That's why our planet and other objects surrounding us orbit around the star. Now, let's keep our attention on the same trampoline. If there's no pressure applied to it, its surface stays flat. Now imagine 2 points on this fabric, symmetrically placed on each side of the trampoline. Looking at them from this perspective, there's no possibility of them ever touching each other. But if an object is heavy enough, this flexible fabric can stretch so much that 2 points might potentially meet. The tunnel between those 2 points would be a wormhole. They're basically bridges that connect two places in the fabric of space and time that have no chance of ever meeting in normal circumstances. Wormholes can also be seen as shortcuts. Problem is, we don't have any of these wormholes in our universe, or at least none that we know of. Scientists have no proof so far that they exist, and we also don't have any idea how they can form to begin with. What we do know so far is that they could, theoretically, exist. To move forward with our story about wormholes, we also need to talk about black holes. They're points in space where gravity has so much force that even light cannot escape them. Gravity here becomes so intense that matter gets squeezed into a tiny space. We know that this can happen when a star, like the Sun, is dying. At the beginning of their lives, a star's hydrogen ignites in its dense, hot core. Because of its gravity, it tries to draw in its own mass into a tiny point. But as long as it has the energy generated by hydrogen fusion, it also pushes objects outward. If we look at it this way, the life of a star is a delicate balance of forces that can last millions or even trillions of years. These forces are also the ones keeping our planet in place and making sure we move constantly at the same speed and trajectory. Once that star's energy is exhausted, the only force remaining is that of gravity. Hence, some stars, those that are big enough, become black holes.
Oh my god!
Since light itself cannot escape their force, we people can't visualize black holes. For the human eye, they're invisible. We need special tools with unique telescopes to help us point them out in the universe. Now back to the wormholes. We have yet to see what a wormhole looks like. But scientists have theorized that they are extremely unstable. Why? Because in simple terms, they're made out of a black hole and a white hole touching each other. Okay, what? And as far as we've studied them by now, black holes at one point become infinitely dense and the pressure becomes unimaginable. Once you enter a black hole, there's little chance you'll make it out the other side. Some astronomers say that even if we could find a wormhole, and we could technically enter it, and it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole popping out like a rubber band that's been stretched too hard. So, wormholes, huh? We haven't seen them, but we do have some math that can back them up. Black holes? We can't technically see them ourselves, but we do have some gadgets that can help us with that. But there are some theories about the universe out there that might have caught your eye in the past too. If you've watched the movie Matrix, you might have heard about the simulation theory. This is one of those hypotheses that doesn't come from scientists, but rather from philosophers. We know that all the information we have surrounding us, sounds, images, texts, and textures of the things we touch are translated to us by our brains. If our brains are the windows to the outside world, who is to say we aren't living inside an illusion? It may sound outrageous, but some famous thinkers of the world have really considered this possibility. The simulation theory can't be listed as a truly scientific one. If it fails the basic test, there's no way to prove if it's true or false. What about life on other planets? There are many scientific projects taking place all over the world looking at ways humankind can survive outside the Earth, should we ever have to. Like the Hot and Mars project, which is taking place on Devon Island, located in the Canadian Arctic archipelago. Conditions here are so harsh that scientists believe if we can make it here, we can survive on Mars too. That's because the soil stays frozen throughout the seasons. Also, the eastern part of the island is covered by a thick ice cap all year round. Since almost no plants are growing here, there are no animals that could have adapted to these conditions. Despite all the scientific effort, some seem to believe there's some sort of life form on Mars already. NASA's Perseverance and Curiosity rovers take regular pictures of the reddish planet's surface. You can check out these pictures on the internet for yourself if you want to. Over time, some odd shapes have appeared here and there in these pictures, making some people believe people are living there already. Back in 2008, one of the rovers took a picture of a rock that looked very much like a female figure. Other photos seem to show animal-shaped figures, utensils, or other Earth-like objects. Again, there's little to no proof of this theory, as rocks can be of all sorts of shapes and sizes. And if you look at the pictures, it does make you wonder. We may find it hard to travel way over there, but we can theorize that our observable universe has an edge and an ending. This fact raised a question for many scientists and philosophers. Could our universe be just one of many existing in a multiverse? One possible scenario depicted to explain the multiverse is trying to imagine a bunch of universes as separate bubbles, constantly coming to be and moving. Since we haven't figured out all the features of the universe we live in, who's to say there aren't many more? As interesting as this theory might be, we have no observable evidence that we live in a world with multiple universes. So far, we can just imagine different bubbles of time and space, where the rules of physics might be different. Some might lack gravity, while others may exist without ever seeing the light.